I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Thank you for these students, this room to work in. I just pray that you be glorified in what we do this day, Lord. In your name I pray. Amen. All right, so we're talking about systems of differential equations, right? So, let me just try to remind you basically our terminology here. So we're looking at dependent variables, x1, x2, all the way out to xn. Our independent variable is going to be, for the most part, t for time. Although, of course, you could suppose it was something other than time. And the problem we're trying to solve is, what we do is we take these dependent variables and we put them all together into a vector like this. So x1, x2, xn, all right? And basically our goal is to learn how to solve dx dt equals to ax plus f. All right, this is the system of n first order ODEs in so-called normal form. All right. Now, actually, to be more honest with you, I can be a little bit more. Our goal is to solve that, right? But to be a little bit more specific, we're primarily our focus for now, at least, is A is a constant matrix. All right. And also, for the moment being, we're going to assume that f is equal to 0. All right. So that makes the problem we're trying to solve really just dx dt equal to ax. This is a homogeneous system. All right. So I need to define some concepts here. I want to give you a theoretical overview. I'll try to keep it brief as I can, but I do want to explain to you sort of the big picture of what we're doing. So let me just put some. I got to talk about linear independence again a little bit. So what's this? I mean, first of all, a couple things we need to notice. What's the solution? Is a vector of functions now. So, right. In other words, the map t maps to x of t. This is not just one function, it's n functions that we're looking for that simultaneously solve this system. All right? Just like when you're solving a system of equations, you're not looking for one number, you're looking for a set of n numbers which simultaneously solves all n equations you were trying to solve, right? But this is a differential equation, so we're looking for n functions. So it becomes important to understand, when are those functions distinct, right? That's where the concept of linear independence comes into play. So definition, and notice the vector here, x vector 1, x vector 2, x vector, let's say, k. This set of vector functions is linearly independent on, let's say, u, a subset of the reals, when c1 x1 plus c2 x2 plus plus ck xk equals to 0, implies that c1 is c2, ck all 0. In other words, if you have a linear combination of these functions, all right, these vector functions, and it's equal to 0, it must be that that was the trivial combination. Now, I should be a little bit careful here. This is shorthand for a function equation. This is really c1 x1 of t plus c2 x2 of t plus plus ck xk of t equals to 0 for each t in the interval u. That's what this purple statement is shorthand for. It's a function equation. So don't be deceived. That's not just one equation. It's actually infinitely many, one for each time in the interval of consideration. So how do you decide when a vector of functions is linearly independent, right? Let's see here. Check it out. So this equation, the one I just underlined in red, we can rewrite that as follows. That can be rewritten as like x1 glued together with x2 and so forth, glued together with xn times what? Let me give this thing a name, star. So let me just write it out and then I'll try to convince you that I'm not selling you anything. C1, C2, Cn equal to 0, 0. So this is a sum of column vectors with weights C1 through Cn. Depending on which linear algebra book you use, you may learn that this is exactly what we define the matrix column multiplication to encode, this particular linear combination of columns. Anyway, if you've seen it that way, fine. If you haven't, just look at this. If I take this column vector, right, and I multiply it, then I get, as you multiply this out, you get exactly this over here, c1 x1, c2 x2 plus dot dot dot, ck xk. All right? Now, so what we have here is an n by n matrix, all right, of functions. Here we have a column vector. And here we have 0, right? Fine, 0 vector. And what's the condition? The condition of linear independence is that that system of equations, right, has only one solution, the 0 solution for all time in consideration, right? That's the condition of linear independence. So linear independence amounts to only C1, C2, Cn, transpose that, equals to 0, solution for system above for each t in the domain of consideration, u. Now, so if you want the system of equations, right, to have a unique solution, what do you need about the coefficient matrix of the system? Remember, we talked about this before. The determinant, right? The determinant of the coefficient matrix must be non-zero. So we require that the determinant of this thing xn be not equal to 0. All right. On t. Well, on u, let's say. So to be picky, I should put of t, of t, of t, of t, of t. These are all functions of t. And then it's not equal to 0 for all t. Well, actually, no. It would be okay for it to be 0 at some t, but it can't be 0 at all t, to be more clear. So this is the Wronskian for systems. Okay, so this is basically what we call, this altogether is the Wronskian. Wronskian of, this set, x1, x2. And now I'm talking about n functions. I started by talking about the linear independence of k things I've now decided to put k equal to n to make it interesting. All right. So you can talk about the linear independence of 2 functions or 3 functions if you're in like a if you have 4 dependent variables. I mean, you can talk about the linear independence or dependence of as many functions as you like, right? It's just from linear algebra, basically, we know that if you're in a 5-dimensional space and you got 6, then, well, oh, I should be careful though. We're not in a 5-dimensional space. That's the thing. We're in function space. This is infinite dimensional. You can pretty much have as many functions as you want being linearly independent. However, when we talk about functions which are also solutions to a differential equation, if the differential equation has order n, right, it turns out a very similar theorem is going to be true. We have n linearly independent functions that we're looking for to form the solution set. So it's a strong analogy to what we already did for like a particular differential equation, more or less the same story for systems. But, you know, we're talking about vectors rather than, so let me just give you an example here. Something that maybe is always a little bit surprising. Example, we could have x1 equal to 1, 1, 1. We could have x2 equal to e to the t times 1, 1, 1. All right. In other words, that is just a snazzy way of writing e to the t, e to the t, e to the t, all right? And we could have x3 equal to e to the t times 1, 0, 0. These both have an e to the t on them, all right? Yet this is they're linearly independent. They both have the same sort of, the first 2 vectors both have a 1, 1, 1 direction, if you will. But these are linearly independent because this has got an e to the t and that one doesn't. So we pick up the linear independence of vectors in this discussion, but we still have with us the linear independence of different functions. Like 1 is linearly independent from e to the t. E to the t is linearly independent from e to the 2t. These are distinct functions. So we get to enjoy both kinds of linear independence. Linear independence of vectors, but also the linear independence of functions. Both of those are available to us here as we find different kinds of solutions to systems. Now, just to be, you know, what would the Wronskian here be? The determinant of 1, 1, 1, e to the t, e to the t, e to the t, e to the t, 0, 0. Let's see, the easiest thing for me to do is to expand on the last column, right? I don't know, maybe I'm wrong about these being linearly independent, though. My spider sense is tingling. Let's see here. Plus, minus, plus. So that's e to the t. Determinant. I did plus, minus, plus to get the plus e to the t. And so I'm expanding here. So this is the subdeterminant. So determinant of 1, 1. Man, I think I'm wrong. Yeah, I'm wrong. Oh, man. Curses. Well, these are linearly dependent. Huh. Oh, man, there's something I'm forgetting. Well, I'm not going to belabor that. These do happen to be why did I do that? Let me just fix this and let me make this more interesting. Make this be a 0 there. Now everything's good. I'll have to think more about what went wrong with my comment. So that's e to the t times what? Times, yeah. So that's minus e to the 2t, which of course is not equal to 0. So we do have linear independence of those functions. The first function being a constant function. But okay. So let me just get to the point here. So this is what we mean by linear independence of vector functions. They can be linearly independent in kind of surprising ways. What's the theorem? The theorem, what are we looking for?
Before you move on, quick, so the Wronskian being equal to 0 implies what?
Linear dependence. Yeah. It's subtle for the same reasons it was subtle before. It might imply linear dependence. It might imply that there are two different linear dependencies on different parts of the set. And if there's two distinct linear dependencies on the different parts of the interval we're considering, then they're still linearly independent. Like x and absolute value of x are linearly independent, despite the fact that they're linearly independent on the reals, but they're linearly dependent on either the positive or the negative reals.
So, I mean, it's not designed to comment when it is equal to 0, just when it's not equal.
Mostly when it's not equal to 0 is what we're looking for, yeah, because then you get, when it's not equal to 0, that means that this set of vector functions is linearly independent. And it also means that you can put all these vectors together and form something called the fundamental solution matrix. So, definition. If we study dx dt equals to ax, all right, has n linearly independent solutions, x1 vector, x2 vector, xn vector, then big X, which is the concatenation of these, x1, x2, xn, is a so-called fundamental solution matrix. So here's the theorem. If dx dt equals to ax is nth order system, and x1, x2, xn are linearly independent solutions on the reals, then, and I'm being, there's a more general theorem I could state for like when you had the coefficient matrix not being, I'm assuming that A is a constant matrix, okay? This theorem could be stated in greater generality. When the matrix is not a constant but it has functions in it, you could think about analytic functions, you could think about like the smallest common domain, and you could say things about the solution with respect to that domain. Forget about all that. I mean, there's a more complicated version of this theorem, but I just want to talk about when it's a constant matrix, then it turns out the solutions exist not just for some interval of the reals, but for the whole real number system. Just like we had in the constant coefficient solutions, right? We had exponentials, we had sines, we had cosines, we had polynomials. What's the domain of those things? Nothing complicated, right? It's just the reals every single stupid time. It's not like the Frobenius problem with these weirdo half-ray solutions like we found, right? We're past that at the moment. Back to our happy place, constants. And so the solutions are going to be good for the whole real line. So suppose you have n linearly independent solutions defined on the reals, all right? Then x equal to c1x1 plus c2x2 plus plus cnxn is the general solution. Now this I could also rewrite as x times c. Using my fundamental matrix notation. Right, that's also the fundamental solution matrix times a constant vector, c. Do you guys see that? Like, if I take this matrix times the column vector c1, c2, cn, I get back this linear combination again. So you got these two different ways of thinking about it. So basically, let me just kind of encapsulate the whole thought process here. What we're after, you want to look at it, you can look at it a couple different ways, but here's basically the game plan going forward. For a system of differential equations, our goal is to find n linearly independent solutions to the system. Just like our goal in the nth order problem was to find n linearly independent functions. Right? We need to find independent functions, and we need to find n of them in order to encapsulate all possible initial conditions. If you give me an initial condition, right, then the solution, there's a unique solution for that initial condition. That's also a theorem we have. The cool thing now is, another way you could look at it is we're just looking for a matrix, right, where every column is a solution to the homogeneous problem, and that's an invertible matrix, which is easy enough to describe, right? The determinant's non-zero. All right. So we don't really need this matrix concept just yet. I'm introducing it here so that you can get used to it. And the idea of the matrix, looking for the solution matrix, will become more important to us when we get towards the end of this discussion. I'm just throwing it out there now so it's not totally weird when we get to it later. Okay? And I may exhibit solution matrices as we go through and solve some problems in here. All right, so that's the problem. This is the big picture. Now let's solve some problems, actually. So how do we solve them? So this is the eigenvector technique. So to solve dx dt equals to ax, we propose that the solution have the following form: x equal to e to the lambda t times some vector u. All right, so at the end of last class, I worked out what that means. Let's work it out again. So if this is going to be, this is a solution, I'm proposing the solution has this form, where lambda is some yet to be determined scalar, all right? And what does that mean? That means that d dt of e to the lambda t, u, is equal to a times e to the lambda t times u. So you differentiate. Differentiating gives you lambda e to the lambda t u. And over here, we can pull the scalar out, e to the lambda t times au. Remember, A is a matrix here, square matrix. N by n constant matrix, just to remember. I've said this, but let me say it again. It should be emphasized. That's what A is. It's an n by n constant matrix. So you guys see what happens. E to the lambda t, we know this. We've played with this before. We know it's non-zero even when lambda's complex, right? Things is non-zero. So we can divide by that without loss of generality. And what's it to give us? Lambda u equals to au. Beneshu. Now, if you've had linear algebra before, you should recognize this as the condition that u be an eigenvector of A with eigenvalue lambda, right? If this has u not equal to 0, this defines u as an eigenvector. An eigenvector is just fancy word. I mean, I think it's basically German for proper vector or characteristic vector. Anyway, so I usually will just abbreviate that to E vector. It's an eigenvector with eigenvalue. And I'm just going to write E value because I get tired of writing eigen lambda. I need to show you guys a little bit more linear algebra for us to appreciate the structure of this. So this is really the same as what? A u minus lambda u equals to 0, right? So I can rewrite that as A minus lambda times the identity matrix times u equal to 0. here's the thing about that equation. That's a homogeneous equation. All right? There's always a solution to this, which is just u equals to 0, right? But we're insisting that there be a second solution, the eigenvector solution. Eigenvectors are non-zero, all right? So we're saying that this equation has at least two solutions. Now when you're working over the reals or the complex numbers, if it's got two solutions, guess what? It's got infinitely many. So we're necessarily in the case that A minus lambda I cannot be an invertible matrix. If A minus lambda I was an invertible matrix, I could multiply by the inverse, and I would just get u equal to 0 here as the only solution. But that's not the context we're interested in, is it? We're interested in looking for a non-zero solution to this. So that necessarily implies that the determinant of A minus lambda I must be equal to 0. This, right here, is a nth order polynomial equation. It's an nth order polynomial in lambda, right, whose solutions are the eigenvalues. One of the major tasks of linear algebra is to prove that these eigenvalues exist, and to prove that for each eigenvalue you get an eigenvector, and to explore the theory of that and the structure of that. Turns out, if you have distinct eigenvalues, you get linearly independent eigenvectors paired to each eigenvalue, which is distinct. In the case that the eigenvalues are repeated, it's dangerous. There may or may not be enough eigenvectors. So, this, guys, is basically the theoretical backdrop for us finding solutions. Let's try to put this into practice. I know it's kind of out there a little bit at the moment, but let's look at an example. So let's see here. X prime equals to, let's say, I don't know, x plus 2y, and y prime equals to, let me think about this for a second, x plus 3y. Yeah, that should work out nice. Do you want me to tell you how I know that works out nice? Let me tell you my secret. I'll tell you my secret later. One thing at a time. Remind me to tell you the secret, though, before I get too far past this. So that's the scalar system, right? So our first job here is to convert to a matrix problem, right? Not much to do here. X, y prime equals to 1, 2, 1, 3, xy, right? Now, in this context, what do I have? I've got like x is my x1, and I've got y as my x2, right? I mean, for the theory, I like to use x1 through xn. For actual examples, I like to use xy or xyz. Because I don't know about you, I don't take any particular joy in writing x sub 1, x sub 2, x sub 3. If I can get away with it, it's much easier to write that out. All right, so this is my A. All right. And now I need to calculate its eigenvalues. So let's do it. So the characteristic, well, I don't need to use that language, sorry. Excuse me, characteristic polynomial. Rather, characteristic equation, let's say, is 0 equals to the determinant of A minus lambda I. You got choices here, guys. Some books would do lambda I minus A. Some books do A minus lambda I. The reason I do A minus lambda I is because I don't have to put minuses on all the A's stuff. And when you get to a 3 by 3 matrix, then you have to put minuses on 9 things. That's 9 opportunities to make a mistake, right? When you're just subtracting lambda I, you've just got minuses on the diagonal. less opportunity for making a mistake. But it does make for less natural algebra. So I don't know, this is just the choice I made. You'll see how I undo it in a second here. So we're looking at the determinant of, so this lambda I is lambda with zeros, right? So all that amounts to is subtracting lambda off the diagonal. So I get 1 minus lambda. I'll put some dividers in here. 2, 1, 3 minus lambda. But you guys know how to calculate determinants. So this is 1 minus lambda times 3 minus lambda minus 2. And what I usually do is I just write down lambda minus 1 times lambda minus 3. I just multiply through the minus there because I have easier time thinking about it like that. In fact, I won't even usually write down the step I wrote above. Personally, I typically just skip from here right to there and do that reversal in my head. Because when I multiply, I do better multiplying personally when I multiply things like this as opposed to things like that. I don't know, it's just my personal algebra demons, whatever you want to say. Anyway, lambda squared minus lambda minus 3 lambda plus 3 minus 2. So what you got? You got yourself a lambda squared minus 4 times lambda plus 1.
So you multiplied everything.
That's not cool.
-1 in
It's not cool.
the
Just a second here. I think I did something wrong. See, because I should be getting... Oh. Oh, wait a minute. Wait a minute. No, that's a minus 2 because it's this times that minus that times that. Oh. Phooey. It's my fault. I mean, it's not wrong. It's just not pretty. Can I change the problem? No. Oh, man. You guys are no fun. Let's see once again.
we can change the homework problems.
All right, fine. I'll stick with it. Oh, but I can't stick with it because this is lambda minus 2 squared. What? Minus 3. Well, I guess I can. I'm fine. If that had worked out to a plus, we'd be in trouble. Then we need complex eigenvectors, which I don't want to talk about today. Do that next time. I'd really like this to be prettier than that. If you guys don't mind, I need to tinker with this. I need that 3 to work out to be I want that 3 to be a 4. If that 3 is a 4, then this is not... You guys don't want me to work a problem with square roots all through it. You really don't. How can we make this 3 become a 4?
Just make y 2x plus 3y instead of...
If I put a 2 here, I think that creates other problems. We should mess with the 2. We should mess with that too. I think. Oh, I guess it shouldn't. If I put a... Oh, that's dumb. Oh, fine, I'll just take my medicine. Here it is. Whatever. So this is lambda... Oh, dang it. Equals to 2 plus or minus the square root of 3. It's hideous. Look away. But that can happen. You know, that's how the real world is. It's full of ugly characteristic values. And I just don't want to finish this problem. It's going to... I thought I had this worked out so the eigenvalues would come out to 1 and 4, but obviously I didn't do it right. Oh. let me suffer through it. Here we go. So these are my characteristic values. Let's say lambda plus and minus, or if you like lambda. So like lambda plus 2 plus the square root of 3. Then I will have to solve a minus lambda plus times a vector. Let's say u plus equal to 0. Find the solution to this. Now, what is that? Well, that is what? We lost our cameraman momentarily. Let's see here. Okay, so that is 1 minus parentheses 2 plus root 3. And then there's a 2 here. There's a 1. Then there's a 3 minus parentheses 2 plus root 3. What I do is I use u and v as disposable variables here. So this is my u plus, so to speak. I'm trying to find how that works out. So what's this give us? It gives us minus 1 minus root 3, 1, 2. Down here, 1 minus root 3. Times uv equal to 0, 0. If we did this right, these should be the same equation in disguise. Like, so here we have minus 1 plus root 3 times u plus 2v equals to 0. What happens if you take this equation and you multiply this by 1 minus root 3? What do you get? This times 1 minus root 3 gives me, what's 1 plus root 3 times 1 minus root 3? It's 1 minus 3, right? So this gives me minus 2, excuse me, 1 minus 3 is minus 2, right? So 1 minus 3u plus 2 times 1 minus root 3, v, equal to 0, also known as u plus 1 minus root 3, v equal to 0, which is, by the way, what? So I took the first equation multiplying this out, right? This is the first equation. And what did I just show? I showed if you multiply the first equation by 1 minus root 3, we get the second row, right? So this system is what? It's like the same equation repeated. This more or less has to happen in one sense or another for the 2x2 system. If it's going to have an eigenvector, it can't have two independent equations. If you've got two independent equations, geometrically that means that you've got two lines with dissimilar slopes and they have a unique intersection somewhere. In fact, the origin, since we're talking about lines through the origin. So in order for this to work, in order for us to get an eigenvector solution, there has to be the case that these equations are redundant. And so there's not just one solution. In fact, there are infinitely many. So basically, I can take either one of these equations and use it. I guess I'll use I like the second one as the prettiest for this one. So I got u plus 1 minus root 3 times v equals to 0. So we can just set v equals to 1. Then u is equal to root 3 minus 1. And so u plus, my eigenvector, is exactly root 3 minus 1 and a 1 down here. This is a solution. Multiply by any non-zero number. Still an eigenvector. This is not surprising, right? If we have a u plus equal to lambda plus u plus, right? If you multiply this by c, you can multiply by any non-zero scalar c, right? And that will also solve the same eigenequation. It solves the same condition. So anytime we have an eigenvector solution, we can always rescale it however you like. Your Texas Instrument calculator will give you these weirdo decimal eigenvectors. What they're doing is they're normalizing the length of your vector to 1. So many softwares automatically rescale the eigenvector to have length 1. What you say, like, why did you set v equal to 1? Why did I do that, guys? Just made it easy, right? Just convenience, nothing more than that. All right, now we need to find our other eigenvector. Sorry, this is so hideous. Can I erase? Can I erase this piece? Are you guys good on what I was saying here? So guys, when you're working problems, if you find what you think is an eigenvalue, and you get to this point of finding the eigenvector, and you have not redundant equations, but not, like distinct equations, so only 0 is a solution, what this means is you made a mistake. Okay, so you need to go back and find your mistake. Do not put 0 as an eigenvector unless you just want to convince me you're not paying attention. But I see all your eyes, so I know you heard me. So if you put 0 as an eigenvector, I feel it's just plain disrespectful at this point. Sorry, but in a larger class I could chalk it up to apathy, but here it would be direct defiance. So or I don't know, maybe you're just like self-destructive. It's like academic cutting or something. I don't know. Let's see here. I'm sorry, is that too dark? Let's see here. Let's see here. Lambda minus equals to 2 minus root 3. Don't do it. So then we're solving, I'll just get straight to it. 1 minus 2 minus root 3. And then there's a 2 here. There's a 1 here. 3 minus 2 minus root 3. And u and v are disposable variables. I'll use them again. And so you just pick whichever one you want. I'm going to pick, these are going to be redundant. I did my work right. So I'm going to get u plus 1 plus root 3 times v equals to 0. So set v equals to 1, and we get u equals to minus 1 minus root 3. So u minus will be the vector minus 1 minus root 3, 1. I might ask you, I might have a question like this, but I really prefer to have these work out to integers. And so I'm annoyed with this example at the moment, but I guess it's good because your homework might not always have integers. Fine, fine, fine. You got me. So the solution then, x of t is c1 e to the what? E to the lambda plus, which was 2 plus root 3 times times the u1 vector, which is square root of 3 minus 1, 1, plus c2 e to the 2 minus root 3 t times the u minus vector, which we worked out to minus 1 minus root 3, 1. There you go. That is the solution to this problem. Now, if you want me to go back and tell you what's the scalar solution, right? Like what's actually x's of... Tired of this. If you wanted me to find x as a function of t and y as a function of t, we can get that from this. Right? Like can you extract the scalar solution? This is the vector solution. Oftentimes I ask you guys for the vector solution because I feel like once you're with it, once you know the vector solution, you can easily, it's a routine, and in my opinion, sometimes uninteresting, to find the scalar solution. But since we haven't done it before, let's do it this time. What's the scalar solution now that we found the vector solution? Any questions about this before I erase it? Oh,
when you're doing
actually, I'll leave it. So I can use either one. What do you mean?
when you're
Oh, I could have set, you mean like I could have set u equal to 1,
right.
and then v would have been like uglier. It would have been like 1 over minus 1 over 1 plus root 3. Yeah, that we could have also done.
But just by convention.
Yeah, what I can't do here is I can't set either one of them 0. If I set either one of them 0, it makes the other one 0. That's forbidden. Yeah, it's not so much convention as convenience that I put v equal to 1 here. Look, and when you think about it, right, when you get over here to how we construct the general solution, you see why that ambiguity is not it's not ambiguous at all. Because choosing a different value for the u's and the v's in the construction of the eigenvector just amounts to like rescaling these arbitrary constants in the solution. It's just that. So your freedom to adjust the eigenvector scaling is just reflected in the fact that we have C1s and C2s in the general solution. Everybody agrees on the general solution, is what I'm trying to say. It's just some of us label it differently. Of course, this makes grading these problems challenging, right? So if you were meanie, you just insist that you have eigenvectors that are normalized to length 1.
Also choose to just which the first or the second of equations that you get from multiplying the matrix by the.
Oh, yeah, like which one do I use, this one or that one? I can use whichever one as long as I mean, so what I erased here to show that they were in fact the same equation is I'm being pessimistic in terms of my calculation. I'm kind of like checking, did I make a mistake? When we get to third order problems, actually you should really do row reduction to sort out what the general solution is to be safe, because you can deceive yourself by choosing one equation when you actually haven't taken a full effect of the full system. But for 2 equations and 2 unknowns, it's a nice happy place. There are different things that can happen, but basically you either have the same equation repeated with like a scalar multiple. Sometimes one of them will come out to 0. So you just have one equation to work with. I mean, that's kind of all that happens, I think, if I remember right. I just lost my cap. Oh well. Okay, so the scalar solutions would just be x equals to like c1 e to the ugly exponent t times ugly number root 3 minus 1 plus c2 e to the other ugly exponent 2 minus root 3t times minus 1 minus root 3. And y will be c1 e to the 2 plus root 3t plus c2 e to the 2 minus root 3t times 1. And so there it is. That's the solution to the original problem that we found by the eigenvector technique. Is sneaky? A little bit sneaky. Yeah, they're a problem. As I was saying, oftentimes I just say find a solution. If I just say find a solution, I'm cool with the vector solution. I feel like if you understand the vector solution, you realize that this is entirely the same as that, right? If I say find the vector and the scalar solution, or if I say find the scalar solution, that's what that is. That's the scalar solution, right? Oh, there's the cap. Yes? Mr. Luke. Yeah. In the nth, right? I mean, in the nth order problem, we had to tackle this problem of factoring operators in order to earn the right to say, oh, it's just look at the characteristic equation and factoring, read off the solution set, right? Now here, we have even less calculus to do. Pretty much it's just this e to the lambda t differentiation, right? And the rest of it's matrix algebra, but yeah, and when you get right down to it, most of the calculation here is, of course, just matrix algebra, yeah. Don't worry. We will eventually get back to something that requires more calculus. There's variation of parameters here, too. And it is just as integration heavy as the other one. Okay, so another example. So x prime equals to 2x plus 3y plus y, let's say, and y prime is equal to 2y. Let's try to solve this thing. Was there a question?
I was just trying to remember what the name, so that one was vector.
Oh yeah, this is the vector solution, and this one's the so-called scalar solution because it's, you know, in systems of equations, it would be the difference between writing your solution as the solution is 1, 2, 3, right? The scalar solution is x equals to 1, y equals to 2, z equals to 3. So I think if you know this, you know that. But, you know, some books make a big deal out of you have to put the solution back like this, otherwise it's not really done. I mean, okay, I understand that. The starting point is a scalar system, right? Conceptually. But, I don't know, it's just, for me it's just kind of a drag to always multiply back out. It's just busy work. Once we've done it one time, we know how to do it. And we'll do it from time to time. All right, so this one, let's take a swing at it. See what happens. So here we have xy prime equals to 2, 1, 0, 2, xy. Here's my a. Okay, so let's find out the eigenvalues. Determinant of a minus lambda I is the determinant of 2 minus lambda, 1, 0, 2 minus lambda, also known as lambda minus 2 quantity squared equal to 0. So therefore lambda 1 is equal to lambda 2 is equal to 0. Or you could say lambda plus minus if you like that notation. I usually use 1 and 2. I just use plus and minus in the last problem because it's kind of a nice descriptor of those sort of eigenvalues. So, man, repeated eigenvalue of 2, right? What's that? Oh, 0.
That's why I was like, wait.
Yeah, you're justifiably confused. Yes. It's like the division by 0 I did in Calc 2 yesterday. They caught me on it. It's good. I'm happy when Calc 2 says, hey, you can't divide by 0. You haven't earned that. It's like, thank you. Very good. This is what I want for my Calculus 2 students. All right, so as always, my mistakes are intentional for your learning. But anyway, so let's find the eigenvectors. So we're going to look for, let's say, lambda equals to 2. We're trying to find a minus 2i times, let's say, u1 vector equal to 0. That's what we're trying to find, this vector. And what is that? Check this out, right? It's, so 2 minus 2, 1, 2 minus 2, 0, right? Times uv. Just see, let's clean it up a little bit. In other words, 0, a 1, a 0, a 0. So this is that example I was just talking about. Sometimes the equation works out to sort of not an equation. So if I want to solve this equal to 0, 0, what happens here? 0 times u plus 1 times v equals to 0, right? The second equation is not interesting. Actually, what's interesting is it's not interesting. And this just tells me what? So apparently v is equal to 0, right? You guys have, well, not you guys necessarily, but like the universe of you guys, of people who take differential equations or linear algebra, for some reason, you want to say that this makes u also be 0. But that is not what this says. This just says nothing about u. In other words, u is free. So u is free. Yeah? U is free. Glad to help. So we don't like that. We're going to make it equal to 1. So there we go. So in other words, thus u1 equal to 1, 0 is eigenvector with eigenvalue lambda equal to 2. Where are my other eigenvalues at? They're nowhere. There's just 2. Just 2. And yet the general theory I was telling you guys says that we need 2. Count them 2 linearly independent solutions. But I've just got one thing to make here, right? So we get x1 equal to e to the 2t, right? Times 1, 0 as solution 2 star. Well, let me call this. Here, let me make the interesting ones. I like this one. I don't care about that. Fine. So there you go. Just that one solution. So that's not the... We're missing something, right? So what does this tell us? Math is broken. No, it just means that eigenvectors are not sufficient to generate solution set in all cases. It means we need to look for something else. Something beyond eigenvector solutions is what this means. All right. Now this problem is sufficiently simple. We could take a step back and we could just use brute force techniques to solve this problem. Right? Ignore this eigenvector construction, this elegant linear algebra stuff we've been doing, and just go back to basics and do just hand-to-hand combat with this system. We could find the other solution, right? How would you do that? I mean, just take a step back, strip away the theory, strip away all these techniques that we're working on developing, and just strip it back to its bare bones. This piece right here, this thing, how would you solve this? Uh-huh.
Looks like y has solutions of 1 e times e to the 1 half t. Check that one.
But how did you do that?
Twice. Yeah, I basically looked at it and saw it.
So you said 2 times x prime is equal to 4x plus 2y? No?
I was just looking at the second equation.
The Oh, I'm sorry. Yeah, I'm an idiot. Duh. Why am I making this complicated? Yeah, we can solve... This second equation is already what's called uncoupled. An uncoupled equation just involves one of the dependent variables, not both, right? So you're right, Luke. We could just straight up solve that. This has solution y equals to c1 e to the 2t, right? And then that gives us x prime equals to 2x plus c1 e to the 2t. And that we can solve by the integrating factor method, or whatever floats your boat. But this has solution x of t equals to c2 e to the 2t. But it's got an overlap, right? So I got to guess like xp is equal to t e to the 2t times a, right? So like xp prime is a times 1 plus 2t e to the 2t. And so like, let's see here, working through it, I get xp prime equals to 2xp plus c1 e to the 2t. That is going to give me a times 1 plus 2t e to the 2t equals to 2 at e to the 2t plus c1 e to the 2t. These guys cancel, thankfully, because overlap works. And